Okay, so for the rest of lab 2 we're going to be looking at the petrels data. So I'm going to start off by putting my name in the markdown file, and then we're going to run this first code chunk which will load in the libraries we need and read in the data. And so in this first code block we're going to remind ourselves how to produce a table of sex and area. There's a number of birds of each sex in each area, and also do a box plot to look at the changes in the right wing length between each of these variables. So table, petrels sex, petrels area. Okay, there we go there. So we note that area 5 has the highest proportion of male birds. Area 3 and 6 have the fewest birds. Then we might want to do a box plot. So we'll remember how to do that. Box plot. So we want to put X as the sex and Y as the right wing length. Okay, interesting, we've got some unknowns here. If we want to filter those out, we could run na.omit on the petrels data set, which will get rid of the missingness. Okay, and so we can see here that so on average the right wing length of male birds is a little bit higher than females. Okay, and what about by area? Presumably where we collected the birds is not going to be missing. Okay, and area 5 birds are larger on average than the other areas, but a bit of overlap. Shapes and spreads are similar. Remember, when you're assessing box plots, basically we're looking for kind of the large changes. So you're looking for big shifts compared to the others. So you can see that this one's definitely bigger than the areas 2, 3, 4 and 6, but perhaps not quite so clear with area 1. All right. Okay. So now what we want to assess is whether the what the effective area is, and whether the area, the difference in area is just due to sex. So we see that we see that males are bigger than female birds on average, and we also know from the table that the area 5 in area 5 there were more males as a proportion than females. So it might just be that the size difference we see in area 5 is just because we've got more male birds. And of course this is something that we can test with the linear model, right? Because we can adjust the area effect for sex. And once we do that, if we also see that area 5 is bigger, then we're kind of done. So that's the nice thing about a linear model, over and above doing tests separately. So we're going to first do a linear model with just area in it. So right wing length by area. Let's have a look at that one. Okay, and you can see the overall p-value is really small. So that's telling us that that something in our model is making a difference, or is explaining the right wing length. we can see from the R squared that about 17% of the variation is explained, which isn't a huge amount, but of course we've only got a grouping variable, right? So the only thing we can show is the difference between groups. We can't explain the difference within each group because we've got nothing else to use within each group to explain that difference. And as area is the only thing in the model, area must be important. And we can use the estimate columns in order to note down what the differences are. So we see that area 5 is in fact larger compared to the baseline group, which is area 1, the group that's not there. Area 6 is smaller. In fact, areas 2, 3, 4, and 6 are all smaller than area 1. Okay. Right. So okay, so now we're going to produce a linear model with sex in it instead. In fact, I think I've done these in the wrong order compared to what we're supposed to, but that's okay, no big deal, as long as we get them done. Just to check whether the sex effect is real. Okay, and again, the p-value is small. So sex is important. Note that it's not all that important. It only explains about, just below 2% of the variation. And that makes sense. There's only a small difference. We saw that in our graph. There's only a small difference between the sexes, and that's the only thing that we can explain. The within sex variation we can't explain, right, using sex. Males are larger than females by about 3.1 millimeters. Okay, so now we're going to combine both sex and area in the same linear model. Okay. Okay, so now we can see that again the overall p-value is small. We've explained about 19% of the variation. So something, the overall p-value says something in our model is making a difference. So either sex or area or both are useful. Notice that the group effects of area. So the group effects is that male are again larger, although not as large. So 2 millimeters bigger instead of 3 millimeters bigger up here. So we've moderated the effective male a little bit by explaining the effective area. And similarly, the effective area isn't quite as strong, right? So the area 5 is 3.76 millimeters bigger, and before they were 4 millimeters bigger. So by including the other variable, we've moderated the effect a little bit, but nonetheless the effects are there, right? We can still see that area 5 is larger and the other areas are smaller. So just a little comment about what the equation here is, or what's represented by each of these things. In this case, the intercept is going to represent the baseline for both grouping variables. So it's going to represent females because we have an offset for males, but it's also going to represent area 1. So the 388.1 is going to be females in area 1. Okay, so males in area 1 are going to be 388.1 plus 2, so they'll be 390.2 or thereabouts. Females in area 2 will be the female in area 1 plus the area 2 effect. But to get to males in area 2, we're going to have to add all 3 entries. So we'll go 388 plus the 2 minus the 6, right? Because we need the male effect and the area 2 effect. So that's just something to be aware of. We'll go over this in a little bit more detail in lecture 3. So let's visualize our model. So maybe we'll visualize 2. We'll visualize the one with just area in it by itself. Okay, so that's the effect of just area by itself. Okay, and we'll compare that to the one with area and sex in it. Okay, and so what we see is that we can see the sex effect, but it's quite small. We can see the area effect, and what we notice is that the area effect is basically similar between these two, right? So in this one here, we've controlled for sex, and we basically get the same pattern as if we hadn't controlled for sex. So that's telling me that the effect that we see of area when we didn't control for sex isn't due to sex, right? So area 5 isn't bigger because it has more males, because even once we include the male-female effect, we get the same result. Okay, so okay, and finally, we will look at the diagnostics, maybe of that last one. Okay, right, and recall that we only really have to consider the first one to look for linearity and equal variance, and you can see here that you know, if you look for the trend through here, it's going to be fairly flat, so linearity is okay. And if you look for equal variation, then it's not too bad. It's all kind of the same amount of variation as you go across. Notice the vertical striping that we're getting. That's just because on the x-axis we have the fitted values, right? And the fitted value in this case is going to be the mean within each group. So there's actually only 12 possible values, the 2 sexes and the 6 areas. So that's going to be, you know, male and female in each area, so that's going to be 12 different values, and that's why you get the vertical striping. So this is entirely expected and not something to worry about. The only thing we're looking at is the vertical scatter within those values. So this actually looks fine. Linearity and equal variance look no problem at all. Normality looks okay. Just to note that the residuals here will be will basically be the variation within the male and area subgroups, right? So essentially what we're looking at is it's like looking back at the box plots and saying, are they normally distributed, right? So if the residuals are normally distributed, it's just the distribution of the values within each group is normal. And you can see that actually the you know, the box plots look nice and symmetric within both the sexes and the male and females and the different areas, so that's actually not a problem, and this is what the QQ plot down here is confirming. Don't need to bother with the third one. The fourth one is looking at whether there's any observations that are particularly strong, that have high influence in terms of extreme X values or extreme residuals. Notice that extreme X values in this case would be an extreme group, which we don't have. There's no problem here, no Cook's distance lines on here at all, so we don't have to really worry about that. So the only thing that can really be extreme is the magnitude of the residual within each group. So we've got a few that are large, but nowhere near, so 492 for example, but nowhere near the Cook's distance lines, which must be down sort of over up in the top right or the bottom right. So there's no problem here at all. So in lecture 3, what we'll be doing is we'll be looking at extending this model, essentially allowing the sex effect, so the difference between females and males, to differ between each area. So at the moment we're assuming that the sex effect is the same for each area, so the difference between male and female birds are the same within each area, which might not be the case. So that's what we'll be allowing, and that's what we'll be allowing for in lecture 3.